Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Welcome to the second lecture of Unit 7, Precipitation and Clouds. We start with snow depth measurements from sites across Alaska. We show measurements in the winter of 2011 and 2012. We start with measurements from 6 sites in 6 different climate regions: Anchorage in Cook Inlet, Annette in the southeast panhandle, Bethel in west central, Cordova in south central, Granite Creek in the interior, and Utgarvik, or Barrow, in the Arctic. These 6 sites represent different climate regions and show the large variations in snow depth across the state. In temperate Annette, far south in the Panhandle, there is little snow on the ground. In Bethel, the snow depth increases and decreases, while in Anchorage, Cordova, Granite Creek, and Utgarvik, the snow depth increases over these 2 months. We see that Cordova has the greatest snow depth with near record values in the winter of 2011-2012, while Utgarvik has the least. We see that snow depth does not increase steadily from the warmer south to the colder north. We now show measurements from Fairbanks, McGrath, and Tok in interior, Kodiak in south central, and Turnagain Pass in Cook Inlet. We see that snow depths in Tok and Fairbanks are similar, where both sites sit in the Tanana Valley. There is deeper snow in McGrath to the west of Fairbanks. Turnagain Pass on the Kenai, just south of Anchorage, has significantly more snowfall and deeper snow, reflecting the effect of the mountainous geography in the Kenai, just as in Cordova. Snow appears later in the season in more temperate Kodiak. The measurements highlight the fact that precipitation varies strongly with local geography. The measurements also highlight that snow depth is not a simple record of cumulative snowfall, that snow on the ground can disappear with melting and sublimation over the season and then reappear later in the season as new snowfall occurs.
The overarching question we're addressing in this unit is how do clouds and precipitation form? Their key questions are listed here. Fundamental questions about the nature of clouds. How do they form? How do we classify them? How do they reflect the atmospheric conditions? That can also be used in forecasting, that the type of clouds present warn us at the type of weather that's coming. How do we get from clouds to precipitation? Not all clouds cause precipitation. Can human activities affect precipitation and the nature of the precipitation? And finally, how do weather radars work? Weather radars are an incredibly important tool in capturing real-time precipitation and real-time forecasting, and they've been part of our ability to warn people about severe weather and save lives as they have been developed and perfected in the last 20-30 years. So what are clouds? Water vapor itself is an invisible gas, but clouds are the highly visible collections of water droplets and ice crystals that can remain suspended in the atmosphere. And here we see in January 2008 and July of 2008 a monthly record of cloudiness over the Earth. We see that the Earth is about 60% covered with clouds at any one time. We also see cloudiness associated with major circulation patterns in the atmosphere, the cloudiness associated with the monsoon in July, the lack of clouds associated with the deserts in North Africa and the American Southwest in the summer, and of course Australia appears relatively cloud-free, sunny and dry. We also see that the pattern of clouds across the equator in January moves northward in July. So it moves from the summer hemisphere, the southern hemisphere, northward into the northern hemisphere. And as we look at circulation patterns in later units, we'll see why this happens more directly. How do clouds form? The situation in nature is more complicated than in the laboratory. In the laboratory, our saturation vapor pressures are based on studies of water vapor over flat surfaces of water. In nature, we're talking about condensation into small droplets, and the structure of the droplets changes the way in which water vapor moves back and forth between liquid and vapor. If we have perfectly clean water, we expect that we have to actually supersaturate, relative humidity is greater than 100% to get droplets to form, and indeed this is very difficult, and if this were the case, it would be very hard for clouds to form in nature. In reality, the atmosphere is full of condensation nuclei, either natural condensation nuclei like sea spray, which are small particles in the atmosphere which facilitate condensation at relative humidities less than 100%. We also have condensation nuclei associated with emissions from industrial and human activities. We also have contributions to cloud formation from emissions actually in situ in the atmosphere. Contrails from aircraft are associated with formation of cirrus clouds. Cloud formation is further complicated by the fact that water in droplets can exist in a supercooled state at temperatures below 0 degrees Celsius. In fact, down to temperatures of minus 40 degrees Celsius, you can have liquid water present in the atmosphere in very small droplets. And we'll see later in the unit that this is an important factor in how clouds create precipitation. Cloud formation is complicated. In fact, it's one of the most uncertain aspects of our climate predictions about how the cloud regime of the planet will change because of questions of albedo, but also because of questions of precipitation. What will the impact be if clouds change? What the patterns of precipitation? Precipitation is the biggest challenge in weather. Snow and rain impact your life far more than just changes in temperature alone. How do we classify clouds? We classify clouds based on their appearance, the physical characteristics, and a healthy dose of Latin. We have a whole variety of clouds we can look at. I'm going to just highlight some common clouds that we will encounter this semester. Stratus clouds are an example of low clouds. These are broad uniform cloud layers across the horizon. They're formed of water droplets, and they're formed when a broad layer of air rises gently into the atmosphere and cools and causes the condensation for the clouds to form. Altocumulus clouds, in comparison, are middle layer clouds. The alto meaning that they're higher than low clouds. The cumulus means that they're puffy. They have roll-like patches or puffs. They are formed of water droplets, and they are thick enough to obscure the sun. They don't lead to heavy precipitation. Finally, cumulonimbus clouds are clouds that are puffy and also likely to cause rain. That's where the nimbus comes from. And these clouds have large vertical extent. They are forming in regions where we have an unstable atmosphere, as we saw in the last unit. Issues of stability in the atmosphere, the temperature profile is very important. These clouds form in regions where you can get air parcels rising a significant depth into the atmosphere, large vertical ascent, and we get significant rainfall associated with cumulonimbus clouds, and we associate them with thunderstorms. Cloud formation requires vertical motion. In the upper right panel we see a map of the United States showing cloud formation over the land but not over the Great Lakes, and this is because the land is warmer than the water, and so we're getting heating and rising air over the land and not the water. In the middle panel we see that we can get cloud formation in bands as air comes over mountains, and you get the air traveling from left to right rises over the mountain and then bobs due to buoyancy on the right side of the mountains, and in the rising crests of air we get condensation because we get cooling. In the lower troughs we get evaporation, and so we get bands of clouds that follow the crests in the air motion. In the bottom panel we have an example of cloud formation in wind shear, a Kelvin-Helmholtz instability, where we have wind increasing with height, and so a low wind area and a high wind area, when they're next to each other in height, you get turbulence across the boundary. It's called an instability because it raises the air into the higher wind speed layer and gives us these very distinctive curls in the cloud structure. Finally, in the lower left, something unique to Alaska and the Arctic regions, the formation of noctilucent or night luminous clouds in high summer near a height of 80 kilometers. These clouds get extensively studied in Alaska, and they form because in the summer there's a rising cell in the high atmosphere that again causes cooling and allows ice crystals to form. In fact, the mesosphere is colder in summer than winter for this reason. The ice crystal clouds are visible from the ground only at midnight, and the book does a nice job of discussing the geometry of the clouds that they can be seen. So how do we get from clouds to precipitation? In clouds, the particles are held aloft as a balance between the air resistance force and the gravitational force. In warm clouds, the cloud droplets collide with each other. When they collide with each other, they coalesce and become larger. And as they become larger, their velocities become faster. They get dragged down by gravity. And as they get dragged down, they speed up. They collide with other small droplets. As they speed up, those collisions become more effective, and you get a runaway effect where one lucky droplet manages to scavenge the droplets around it and become a large raindrop. In cold cloud formation, you have a mixture of supercooled water droplets and ice crystals. If you go back to the last unit and look at the saturation vapor pressure relationship with ice and water, ice crystals require a smaller saturation vapor pressure at a given temperature than water droplets. So when an ice crystal is next to a water droplet, it thinks the air is too humid, and so some of that water vapor can attach itself to the ice crystal. At that point, the water vapor has become lower than the saturation vapor pressure over the water droplet. The water droplet now evaporates slightly to fill the water vapor that it thinks should be around it, and therefore you end up with a net transfer of water from the supercooled water droplets toward the ice crystals. The ice crystals continue to grow, they become heavier, just like the large water droplets. They begin to fall out of the sky at the expense of the supercooled liquid droplets. And so these are the two ways in which large liquid droplets can form in warm clouds and large ice crystals can form in mixed phase clouds. The other thing to note about this is that the particles can have quite a adventuresome process of falling out of the cloud. With updrafts and downdrafts, the particles can travel quite a ways through the cloud, and in fact, if we think about hail, which forms in deep thunderstorm clouds, the hail particles show quite a bit of structure because of the formation of ice in different regimes as they pass through the cloud, and so they carry the history of that formation and their journey through the cloud with them. The other thing to note is that the precipitating particles can change in their journey from the bottom of the cloud to the ground. If we think about a snowflake, which is a bunch of ice crystals that have come together, it can arrive at the ground as snow, sleet, freezing rain, or liquid rain, depending on the temperature profile it passes through on its way to the ground. Also, we can have that a liquid water droplet, a raindrop that falls from a cloud, can actually never reach the ground. It may pass through dry air where it re-evaporates and disappears before it reaches the ground. Humans can influence the character of rain and the properties of rain. An example of this is acid rain. Acid rain is formed by release of sulfur and nitrogen-bearing gases into the atmosphere. Those gases dissolve in water and form nitric and sulfuric acid. In the United States, when we look at the acidity of water, the pH, low values of the pH are more acid. The value of natural water is about 5.3. It's slightly acidic due to the dissolving of carbon dioxide in the water to give you carbonic acid. But with industrial processes, we see that we get pHs that are lower, significantly lower, in the eastern United States. And it's two factors at work here. One is the increasing industrialization in the central United States as you go eastward, and the second is that the winds carry from the west to the east across the United States, and so downwind of industrial centers we get significant acidification. Because we get rain out of this acid rain. It's also a big issue in Canada, though the map doesn't show it here. And the decrease in acid rain in the 1990s is associated with environmental regulation, where we decreased emissions of nitrogen-bearing and sulfur-bearing gases into the atmosphere. Weather radar is one of the major technological advances that have improved weather forecasting in recent times. The weather radar detects precipitation very well because the wavelength of the radars is about the size of the precipitating particles. Under that scenario, from basic electromagnetic theory, when you are bouncing radio waves off objects. If the object is around the same size as the wavelength of the wave that you're using, then you're going to get a very strong echo. The echo strength is used to monitor the strength of the precipitation, because the echo is proportional to the amount of droplets present in the air at any one time, which is a measure of the amount of rainfall or snowfall that's occurring. We can also use a Doppler shift to measure the wind and the movement of the weather system. In the Doppler effect, if the object you're looking at is moving toward you and you bounce a radio beam off it, the radio beam's wavelength will become shorter, its frequency will become higher. If the object you bounce the radio beam off is moving away from you, then the wavelength becomes longer, the frequency becomes shorter. So if your radar is sophisticated enough that you can not just look at echoes, but look at the frequency of the echoes, then you can tell if things are moving toward you or away from you, and the speed with which they're moving toward you or away from you. And so this becomes a very powerful way of reaching into storm systems from a distance without having to send in a plane, without sending in humans. You can reach out with radio waves, you can scan the sky in 360 degrees and capture all of the variability in space and time associated with precipitation that may be critical for issues of human safety and protection of property. The two maps in this slide show Alaska and the Pacific Northwest. They show the precipitation measured by weather radar networks in Alaska. You can see that the weather radar network does not cover the whole state. It's clustered in south central, southwestern Alaska, out on the Seward Peninsula, interior Alaska, and southeast. And you can see relatively light rainfall down in Bristol Bay and in southeast Alaska. You compare that to what we see in Washington State. We see much stronger precipitation, much heavier precipitation associated with the deep green echoes and the yellow echoes. I just want to point out that we think of rain gauges as a very simple measurement and direct measurement of rainfall. In the real atmosphere, where we don't have rain falling perfectly vertical, but we have the rain being whipped by the wind, the rain gauges don't always work as we might expect, and they're not quite as accurate as we might expect. So it's an example of a measurement technique that in principle should work perfectly, but again, when it's put out in the real elements, it becomes more challenging, and the interpretation and the accuracy of the method become more challenging. The last thing I wanted to mention is a trend in meteorology where we combine the power of computers and our physical understanding with our measurements. The radars provide instantaneous measurements of precipitation. If we have a physical model of precipitation, we can relate the instantaneous precipitation to the cumulative precipitation, the total amount of water that may have fallen during the day that would be important for understanding if there's a flood risk. And so we can put those physical models into computers by expressing them as mathematical relationships and writing them up as computer programs. And what's very important about this in a meteorological perspective is to have high performance computers that can take the data from multiple weather radars, combine it with the model, and estimate the rainfall relatively accurately, the cumulative rainfall, in real time. So it's the idea of taking disparate data sources, bringing them all together, combining them with physical understanding, and doing it quickly so that you can respond to weather events in real time. Finally, closing thoughts and summary of the unit. The first thing is that clouds are small droplets and ice crystals that are visible, while water vapor is an invisible gas in the atmosphere. Clouds can form in the real atmosphere at relative humidities less than 100% because of the presence of condensation nuclei, which facilitate condensation of water vapor into droplets. If condensation nuclei did not exist in the atmosphere, then it would be quite difficult for cloud droplets to form. Clouds are classified by their appearance and reflect the meteorological processes that form them, and as a result they also reflect the weather that we might expect from them. Cloud formation is tied to vertical motion. Weather is tied to vertical motion. vertical motion and the conditions that allow vertical motion to occur are a very important aspect of weather and climate. We've seen it in the last unit, we've seen it in this unit. Fog is a cloud at the ground, and therefore fog forms when surface air is cooled. Not all clouds cause precipitation. In fact, most of them don't. Particles must be able to grow in size to fall to the ground. Acid rain is an example of how human activities can couple into meteorological processes and impact the environment. The environmental history of the 20th and 21st century really is the story about how human factors now rival natural factors on our planet in impacting the environment. And finally, radar is a critical tool in measuring precipitation. This cannot be understated. The observational capacity that we have with radars to see storms in real time, to monitor the structure of precipitation in real time at high spatial and temporal resolution is critical in the ability of the National Weather Service to make storm forecasts that are an important part of maintaining human safety.